Hello, everyone, and welcome to the SAS Practitioner track. My name is Tim Januszowski. I'm an applied science manager working for Amazon Web Services, and I serve as a director at the International Institute of Forecasters. Today, it is my pleasure to welcome our speakers, Varun and Kedar from SAS. Varun is a senior manager in the AI and ML Center of Excellency at SAS Research and Development, on top of over 10 years of practical experiences in ML and AI. He's published academically and holds a number of patents, I think 4. Kedar is an AI specialist in the same Center of Excellency and SAS Research and Development, and he works on delivering state-of-the-art solutions with using AI and ML. Kedar holds a master's and PhD degree from Duke University and has more than 5 years of practical experiences. In their talk, Varun and Kedar will present forecasting problems of shipments for the consumer packaged good industry using both traditional machine learning and machine learning models. As someone who works with machine learning regular myself, as well as traditional methods, I quite look forward to your presentation. The stage is yours.
Yeah. Thank you, Tim. Hello to everyone from Cary, North Carolina. My name is Varun Valsaraj. So along with my colleague Kedar Prabhudesai, I would like to thank you for joining our presentation on enhancing the shipment forecast for CPG companies using machine learning and demand sensing. So let's get started. So agility is a key enabler for consumer goods packaging companies or CPG companies to make supply chain as an engine for their growth. So the challenge in today's business environment is being able to plan in the midst of increasing volatility. Market conditions are shifting rapidly. New channels are disrupting traditional players. COVID-19 in some cases have accelerated these changes in the past few months. And consumers are demanding for new products with high expectations for product availability. So in order for companies to make their supply chains an engine for their growth, they must be able to execute an agile and efficient response tied to their demand signal. So in order to successfully do this, in our opinion, companies must do 3 things. First, they should be able to sense real-time demand shifts and quickly adjust their fulfillment plans. Secondly, they should be able to use machine learning and other advanced analytical methods to further increase their forecast accuracy in the short-term window. And finally, they should be able to automatically integrate the results into their process for execution without increasing workload or response time. So a high-level overview of a demand sensing process is shown in the next slide. So the primary inputs are the following real-time signals. First, the shipment order history. So based on our experience, we would ideally recommend having around 4 years of shipment order history. Second one is future orders. So the customers of CPG companies such as Walmarts and Targets and so on, so they place their orders in advance. So these are referred to as future orders. So in our case study, most of the orders are placed 2 to 3 days in advance. However, for promotional items, in order to better facilitate planning, future orders are placed up to 1 month in advance. So incorporating these future orders into demand sensing will help you get better forecast accuracies in those short-term time window. The third one is the daily point of sale or POS data and the customer inventory data at the store and the DC. These can be a successful demand sensing signals. So the customers of CPG companies, they place their orders in response to these POS demand and the inventory on hand. So if the inventory on hand is high, then the customers will not place any shipment orders despite robust POS demand. So it is very important to consider both point of sale and also the inventory data in the demand sensing process. In our new implementation post COVID-19 at SAS, we have also successfully used Google Trends as an optional input to keep track of the shutdown and reopening in regions due to COVID-19. So these input data are then fed through an ensemble of machine learning and traditional time series modeled to generate weekly forecast, which are then broken down to a daily forecast. The resulting enhanced forecast is then automatically integrated back to the current supply chain planning process. So the key goal of the demand sensing process is to obtain an accurate daily forecast. So we have seen that many CPG companies, they invest a lot of time and effort into creating a more accurate weekly forecast and then pass it downstream to the operation team, who then use naive methods such as just evenly dividing the weekly forecast to get a daily forecast. So using such simple techniques usually result in bad forecast accuracy at the daily level and also poor supply chain execution. So it is very important for the forecasting team to own the whole process and use advanced analytics techniques into the entire forecasting process to enable companies' ability to drive an agile and efficient supply chain response to volatility. So the key benefits of the demand sensing capabilities are shown in the next slide. Yeah, the first key benefit is increasing the revenue. So understanding how demand is shifting allow companies to adjust their execution plans to meet the demand needs and the sell through more products and thereby increasing the revenue. The second benefit is reducing the cost. So retail and CPG companies are facing more and more cost pressures driven by rising transportation costs and constrained capacity of drivers. So with a better short-term forecast, company can better plan the transportation needs utilizing their core carriers with the lowest negotiated rate instead of secondary or third tier carriers. So those who are familiar with the lean supply chain concept knows that the moment of products is a waste. The redeployment of product from DC to DC to meet the demands in another region because the original plan was not correct, um, that that incorrectly doubles the moves and erodes the profit. So better planning reduces also the need for expedited shipments to meet the demand. And finally, improved forecast accuracy can also allow companies to reduce their safety stock, allowing them to lower their inventory. The third benefit of demand sensing is improved customer service levels. Demand sensing improves supply chain execution and reduce delays to shipments. So this will help companies improve their customer service levels and drive improvement to their on-shelf availability. So this improved on-shelf availability ensures that the customers can find the product when and where they are looking for, thereby improving their customer service and satisfaction. So let me now hand it over to my colleague Kedar Prabhudesai to walk you through the methodology in detail. Over to you,
Thank
Kedar.
you very much. Yeah, so let's walk through the process that we use to generate these enhanced weekly and daily forecasts. So first we want to just give a very high level overview of the entire process, and then we'll go into specific details for each of these important components and also present some results for each of these. So the main goal with this approach is to use demand sensing signals and machine learning to generate weekly and daily forecast. So the way we do this is first we generate an enhanced weekly forecast. So this block diagram is essentially just summarizing the key aspects to that. So we start with the input data, and essentially this input data is the input time series associated with the product shipments. And we do some minor pre-processing just to prepare it so that it can be used into the models. And then we use a set of two different models in order to generate a forecast. So the first set of models is the traditional classical time series based forecasting models. So you can think of like the ARIMA, exponential smoothing models, and so on, which we are so familiar with and have been using it for such a long time. The second set of models is the machine learning based models, which we use to generate a forecast. Now, the motivation behind using these two different set of models is each product shipment has different characteristics of shipments, right? There may be some shipments which have a very strong seasonal information, which may be very easy to capture using like classical time series based forecasting methods. But there may be some other shipments, some other products, which have very complex patterns, which a time series model may not be able to capture. So we want to use the new advanced machine learning based forecasting models in order to generate that forecast. Now, we use these two different models to generate a forecast, and for each time series, we evaluate the performance of this model, of these two models, and we choose the best model based on the model that performs the most accurate to generate a forecast over a forecast horizon, which gives us the enhanced weekly forecast. And of course, in the next slide, we'll discuss in detail exactly how we generate the machine learning based forecast. But this process allows us to generate a more accurate weekly forecast. Now, as Varun mentioned previously, weekly forecasts are great, but in order to really drive an effective supply chain, you really need a short-term daily forecast. So how do you go from a weekly forecast to a daily forecast? So we use this process of disaggregation or breakdown, where essentially we take the weekly forecast and we multiply it by proportions over 7 days, which we can use to multiply that enhance weekly forecast in order to generate a daily forecast. Once again, for this process, we use different models, which we'll go into detail as we go through this presentation. But here again, the motivation is different products have different daily order patterns. Some may have very long seasonal patterns, which may be able to capture using the seasonal model. Some others may have very short-term patterns, which can be captured using a trend model, while others may benefit by using a machine learning model. So again, we go through this process of using different techniques to generate breakdown proportions, to split the weekly forecast into daily forecast, and again, go through this process of model selection, where we select a champion model based on the best performing of these three models to break down the weekly forecast to the daily forecast. So this is kind of the very high level overview of what we are going to do, and we'll go into specific details as we move forward. So first, let's just focus on generating the weekly forecast, right? So let's focus on the top flowchart here. Specifically, let's discuss in detail how we generate the machine learning based forecast. So here's a flowchart to generate a machine learning forecast. So the first step to generate a machine learning based forecast is to use actually a time series forecast. So this approach, so we first just take the time series data and we fit a time series model over the order history data in order to generate predictions into the future. So the time series model gives us trend information and also actual forecast estimates. These are actually then fed into a neural network based model, along with some other additional attributes about the time series, like what is the product hierarchy associated with a given time series. And also we feed information about the 4-year order lags. And what we mean by that is, if we are forecasting a quantity for a given week this year, we are going to look at what were the order quantities for the same week over the last 4 years. And so these are the various inputs that are used in the neural network model. Now, this neural network is a single hidden layer based neural network, which then actually generates a forecast for a given week, and then it actually splits into these two sections. So we use the neural network predictions, but over the training data, we also evaluate the error terms or the residuals between the neural network predictions and the actual order quantity data. Now, taking these residuals, we actually fit another time series model over these residuals in order to generate a forecast of the residuals. So, and then eventually we just combine the neural network predictions with the residual predictions, which gives us the final machine learning based forecast. So this methodology uses machine learning, but it also uses traditional based methods, because the traditional model may be able to capture some of those seasonal based information or trend based information that time series models are best able to capture. But let's say in the 4-year order history data, there may be some nonlinear relations which may not be able to be captured using a time series model, but using something like a neural network here allows us to do that and generate a machine learning based forecast. Now, before we move on to the specific details, let's quickly get a quick summary of the data. So we conducted this, we used this approach with a large CPG company here in the United States to basically generate more accurate weekly and daily forecasts. So let's walk through some of the data sets that we are working with. So here is a representation of how the data was structured. So imagine there are several products which are essentially shipped from different distribution centers which are associated with the CPG company. And from there, they are shipped to the customer distribution centers. The customers are the CPG end user customers, like the big chains of like grocery stores where you actually find the product, right? So you can imagine like there is a time series associated with each triplet of product, shipping location, and customer location. So this is the time series that essentially we are working with, and the goal is to generate a forecast for this given time series, right? So the main inputs that we used for the modeling are the order shipment history, which is over the last 4 to 5 years, we look at what the order shipments are. Then also the future open orders, which are placed by the customers. And then for a specific customer, we also work with the point of sale and customer inventory data, which were also used as inputs into the model. Now, the CPG company has their own version of forecasts. They do forecasts for predicting the shipments. So they gave us these two forecasts to compare forecasts that we generate with the existing forecasts. So the first one is what we call the FC base forecast. That is using, this is the base forecast that the CPG company generates. It uses classical time series methods, no machine learning enhancements. And then there is also this FC base plus expert forecast. Now the forecast that the CPG company generates, they are typically evaluated by the demand planners. And these are expert folks who have very good sense of what product demand is going to be. And they tweak the forecast in order to make it better, right? So the goal of the approach that we are presenting here is to improve the forecast compared to FC base and FC base plus expert. And we just want to note that the CPG company provided us these forecasts only at the weekly level. We used a different method to evaluate our daily forecast, which we'll come to as we come to that part. Now, how did we actually work with the data in order to generate these forecasts, right? So as we mentioned in the previous slide, we have the input data, which corresponds to the shipment history, the point of sale inventory, and also the future open orders data. And since we have this entire data set, we want to perform this operation of back testing, right? Where we want to split this data and use our models to generate a forecast and evaluate how good our models are over this data itself. So we generated what we call multiple rolling forecast. So essentially what we do is we choose a given start date where all the data after the start date is what we consider as the forecast horizon over which we are going to evaluate the final forecast. The data before the start date, we split into, again, two sets, training and validation. We use the training data to actually train the machine learning models and also the time series based models. And we generate a forecast over the validation period, right? In this validation period, we evaluate the performance of both of these models, and we choose which is the best suitable model for a given time series. Right? Then once we have selected the best model, we combine the training and validation data in order to generate the true out of sample forecast over the testing period. Now, the CPG company, the way they operate is they generate forecasts since as new data comes in, they update their existing forecast, right? So that's the same thing that we do. We just increment our start date to a future period and do this again, the same operation where we're using the training data, validation data, and testing data. And this way we generate multiple rolling forecasts in order to generate and generate these multiple forecasts. Now, in order to compare just the performance for each of these over the testing period, we introduced this concept of lags, which is just a normalized version where you can just compare the forecast for lags 0 through 11 for each rolling forecast and check how good the model is for over each of these lags. So the results that you'll be seeing will be presented as performance over these multiple lags. Okay. Now, for forecast performance, we use two different metrics to evaluate the forecast performance. First one is the accuracy metric, which is, of course, based on the absolute error between the forecasted quantity and the actual order quantity and divided by the forecast order quantity. And we do this, the operation of summation in order to aggregate this data over a time period in order to generate the accuracy values. The second metric that we use is the bias metric, which essentially takes into account the ratio of the 1 minus the ratio of the order quantities over the forecasted quantity. Now, the bias term essentially can be positive or negative, and it can tell whether the forecast is over forecasting. A positive bias corresponds to an over forecast. A negative bias corresponds to an under forecast. Ideally, we want the bias to be as close to 0 so that, because over forecast and under forecast have their own kind of pros and cons. So the results that you'll be seeing today will be these accuracy and bias measurements. So with that, let me hand it over to Varun to walk you through the weekly results.
Yeah, thanks, Kedar. Can we go to the next slide, please? Yeah, let's now review the results of the weekly forecast improvement due to demand sensing. Let's first start with the line chart on the left. So the blue line indicates the base statistical forecast, while the orange line indicates the statistical forecast that has been augmented with the overrides that has been placed by the planners. So we refer to them as a base plus expert forecast. Please note that the CPG companies did not archive their forecast for lag period 7. So if you were noticing an anomaly that why the data doesn't exist. So we have not included the lag period 7 in our analysis. So that has been excluded. So the forecast value add, a concept developed by Mike Gilliland at SAS, is a very effective way to measure the value that has been added by planners. So as you can see here, if you just compare the base forecast and the base plus expert forecast, you can see that in the short term, that is between lag period 1 to lag period 4. So there is a positive value that has been added due to the overrides placed by the planners. But there is minimal to negative value add due to the planner overrides from lag period 5 to lag period 8. And this makes sense as the planners have better visibility in the short term than the long term. So they add much more value in the short term. It also makes a case for the planners to trust the statistical forecast over the longer term and be very selective about where they place the overrides in the longer term, because here we don't see too much value that has been added in the longer term due to the planner overrides. So the enhanced forecast that has been created, produced by the machine learning and demand sensing, is shown in the gray line. As you can clearly see from the line chart on the left, right, the enhanced forecast is more accurate than both the base and the base plus the expert forecast across all the 8 lag periods. So there is definitely a consistent value due to demand sensing. So base plus expert forecast is what is used currently by the CPG company in their supply chain operations. So let us look at the forecast improvement over it a bit more in detail in the bar chart that is actually shown on the right. So the bar chart indicate the improvements that you see using the enhanced forecast over the base plus expert forecast. So as you can see, the enhanced forecast is 5 to 6% more accurate in the short term, that is between lag periods 1 to 4, and between 4 to 14% between lag period 5 to 8. Lag period 5 is a bit of an outlier. I mean, there's a significant drop in the base and the base plus expert forecast accuracy in lag period 5, which we do not see for the enhanced forecast. So it's enhanced forecast is performing well even lag period 5. So we're not clear why the base and the base plus expert forecast had a lower accuracy during that period of time. So because of that outlier, the overall accuracy improvement only during that period was 14%, which was a bit too higher. But overall, if you see the performance across the 8 lag periods, we see a consistent and a significant weekly forecast accuracy improvement due to demand sensing. So let's review the bias results in the next slide. Yeah, thanks, Kedar. So what you see here is the weekly forecast bias comparison. So as Kedar mentioned, a positive bias implies that you're over forecasting. That means that you are forecasting more than the actual shipments. So in these scenarios, you tend to carry more inventory than required. On the other hand, a negative bias implies that you are forecasting less than the actual, which means that you are missing out on potential shipments, which would result in lost sales and reduced service levels for the end customer. So ideally, you want the bias to be as close to zero as possible. So as you can see from the line chart here, the enhanced forecast, which is shown in the gray line, has a bias which is close to zero in the lag period 1 to 4, while it has a positive bias from lag period 5 to 8, but it's under 5%. The base statistical forecast and the base plus enhanced forecast, which is shown in the blue and the orange lines respectively, has a significant under forecast bias across the lag period 1 to 8. So even from a forecast bias point of view too, the enhanced forecast produced using demand sensing is performing much better. So let me now hand it over to my colleague Kedar to talk about the improvements due to adding point of sale data and the inventory data.
Thanks, Varun. So yeah, let's kind of look at the point of sale and inventory data analysis. Now, just let's reiterate what we saw before in terms of the data that is provided. So these are the different levels which we can use for forecasting. Now, if we look at the data that is controlled or which is under control of the CPG company, the order shipment history, future orders, and also the forecast, like the base and the base plus export forecast, these are all data sets that the CPG works with, and we can easily acquire that data from the CPG company. On the other hand, if you think of the point of sale data and customer inventory data, these data sets are very specific to each of the CPG customers. Different customers have different ways of managing the data. So you can imagine just acquiring that data to use for analysis can be very challenging. But one thing is for sure that point of sale and inventory data is a great predictor and very valuable demand sensing signal for shipment forecast, because you can use the lag-based information from the point of sale data, where the lags are proportional to the lead time, and use that as a causal into the forecasting model. However, there are several challenges associated by acquiring this data, because if the CPG customer has data which is stored in a different system compared to the CPG company, there needs to be a mapping associated with each product, so that there is harmony between the CPG data and the customer data. Likewise, every CPG customer has a different IT infrastructure and requires a lot of maintenance and storage costs. And more importantly, the CPG customer has to be willing to provide this data to the CPG company, because this is a very valuable data set, and not all customers may be available, may be ready to provide this information to the CPG company. So for this specific project, we had the POS and inventory data for a very limited time period. We didn't have it for the entire period that we had the order shipment history, and we had it available only for one specific customer. So we did a subset analysis where we included the POS and inventory data into the forecasting model and evaluated its effect on the forecast accuracy. So here is a comparison of the forecast accuracy with including the point of sale and inventory data and not including it. So on the left, you see that in the blue line chart is showing the accuracy with using the same methodology that we discussed previously by using the machine learning and traditional methods, but it only uses the order history data as the input, whereas the orange line corresponds to the accuracy by using the order history data and the point of sale and inventory data. And as you can see that by including this additional sources of information, these important demand sensing signals, there is a lift in accuracy compared to the accuracy by excluding this data set. And of course, these accuracy improvements are not as are different from what you saw previously, because this evaluation was done on a limited data set over a limited time period, since we did not have the data available for all the customers. But nonetheless, we see that for each lag, there is a positive accuracy improvement anywhere in the order from 1 to 1.5% compared to the accuracy by not including this point of sale and inventory data. We observe that this accuracy is mostly impacted by the near-term forecast, that is the forecast in the lag period 0 through 5. And we believe mostly the reason for this is the point of sale data is strongly reflecting the demand and being a good predictor of demand over the lag period 0 to 5, but not as much over the lag 6 through 8. And so, but we do believe that including this data into the forecasting model really helps improve the overall accuracy. Okay, so this concludes our discussion about the weekly forecast accuracy and weekly forecast. Now we want to take this weekly forecast and disaggregate or break down into a daily forecast. Now, the very obvious question that we come is, why not directly forecast at the daily level? Now, what we observe is if we look at the demand history data at the daily level, it is very noisy. There are a lot of fluctuations because the CPG company has a specific pattern in which it ships its products. It may not ship on specific days for which the shipment history data is just going to be 0. So you can imagine there are a lot of fluctuations at the daily level, which really makes it hard for any forecasting model to directly forecast at that level. But if you aggregate this level to the weekly, you get some smoothing of those fluctuations and they are easy to predict. So that's why we take this approach of taking the weekly forecast and we multiply that weekly forecast by disaggregation proportions in order to generate a daily forecast. So just to give a very naive example, and this is actually how the CPG company uses an approach to split the weekly forecast to daily forecast. So let's say for this week, the week of October 26, the weekly forecast prediction is of 1,400 shipments. And for each days of the week, you do an even split of 1/7 in order to generate a daily forecast for each day, right? But as you can imagine, this is not a very effective approach of generating these breakdown proportions. So we have developed some additional techniques to better infer these proportions. So, so in this slide, we are summarizing the approach. So we use 3 different methods to infer the breakdown proportions to disaggregate the weekly forecast to a daily forecast. These proportions are basically inferred from the order shipment history data and also the future orders and POS information in order to generate these breakdown proportions, which you can then use to generate a daily forecast by simply multiplying it with the weekly forecast. And then you go through the process of model selection, where we are evaluating the performance of each of these 3 models over the validation period and selecting the best model that will be used to generate the daily forecast. So in the next few slides, let's discuss each of these models in detail. So the first model is a short-term trend model. So the goal is for a given week to generate a breakdown proportions that we'll use to multiply the weekly forecast. So one way in which you can do it is look at the daily proportions over the last 13 weeks. Right. So here is just a pictorial depiction of what those the daily proportions for each of the previous 13 weeks are, and get the average proportions based on that. Now, once you get these average proportions, you can multiply it with the enhanced weekly forecast to generate that daily forecast. Now, of course, here for simplicity, we have just shown this, just taking the average proportion, but you can also do some, you can incorporate some additional rules while generating the proportions, because you don't want to just take a straight average. Let's say in the previous 13 weeks, there may be one off week where usually over the 13 weeks, they have some specific days over which they are ordering. But one week, there is something that happened with the shipping and they just ordered on some different days than they used to. So you don't want those outliers to really impact what those average proportions are. So you can incorporate some additional tricks, like for example, you look at what are the probability of having a order for a given day of the week based on these previous 13 weeks, and also incorporate that into the model in order to adjust these average proportions over the 13 weeks. So this is the first model that we use. In the second model, we use a seasonal based approach where there are some products which have very consistent patterns over the entire, which are reflected year by year, right? So instead of looking at a short-term 13-week period, we look at a long-term 3-year period. So for a given week in a year, we look at what was the daily order proportions for over the last 3 years. And based on those daily order proportions, we come up with average proportions for a given year and given week, which we can use to multiply the enhanced weekly forecast to eventually generate the enhanced daily forecast, right? So this is the second model. And finally is the machine learning based model, where instead of taking a simple average and just doing a simple breakdown, use a neural network where the inputs to a neural network are the daily proportions over the last 2 years, which are used to predict the daily proportion for the next year, right? And so in order to train this neural network, let's say you want to predict these proportions for 2019, you would train the neural network to predict proportions for 2018 based on the data from 2016 and 2017 as the training phase. And then in the testing phase, you'd feed the data from 2017 and 2018 in order to predict proportions for 2019, which you can then use to multiply with the weekly forecast in order to generate the enhanced daily forecast. Now, so these are the 3 methods that we use, and then we use the process of champion model selection, where we evaluate the performance of each of these models over the validation period in order to choose the best model specific to a time series in order to break down the weekly data into the daily data. So let's look at some results. So first is the daily forecast accuracy, similar to what we saw in the weekly results. But now the lag periods on the x-axis do not correspond to weeks, but they correspond to days. And in this case, they correspond to 30 days. The line chart in blue corresponds to the enhanced daily forecast using the methodology that we just showed in the previous slides with the 3 models. And the line in green is a naive daily forecast where we take the FC base plus expert forecast that the CPG company provided, and we did a simple even split where we just evenly distribute that weekly forecast into the 7-day windows and generate a forecast. And so here you can see that compared to the naive method, the enhanced daily forecast method is much better with a improvement in accuracy of almost like 30%, with the average accuracy of around 76% compared to the naive based methods accuracy average of around 46%. Similarly, with the bias, we see that the enhanced daily forecast bias is somewhere between -10 to +10. So it does fluctuate over multiple days. And we believe that, so if you recall the weekly forecast bias results, they were more or less consistent. Here, there are more fluctuations, which we do expect to happen because you're not always going to get the best breakdown. There may be some days where the forecast is either under forecasting, whereas for some other days it is over forecasting. But if you compare it to the naive method, once again, the naive daily forecast has a much negative bias, which is going from a negative range of -10 to -30%. And it has a huge fluctuations. For some of the days, it's really going up to the positives. And the reason for these spikes is actually can be explained really well, because what's happening is there are some days of the week where the CPG company does not order at all. So it's basically zero. But if you do an even split, you will get a non-zero quantity for that day as a forecast. And so that really accounts for a huge spike in bias. So it makes the bias really high, right? And so on the right, you see that the average bias is 0.3 for the daily enhanced daily forecast, whereas it is -5% with a huge variation over the 30-day period with the enhanced daily forecast. So this concludes our talk. So we just want to give the high-level points and summarize. So we have presented a way to incorporate demand sensing signals and machine learning and shown that it can help improve shipment forecasts for CPG companies. In terms of the weekly forecast, we showed accuracy improvements between 5 to 14% compared to the existing forecast that the CPG company used, which is the FC Base Plus Expert. In the daily forecast, the accuracy improvement was much higher, up to 30% compared to the naive forecast. By utilizing the point of sale information and the inventory information, provides a lift to the accuracy, and we demonstrate that an average forecast accuracy improvement of around 1% is observed by including these data sets and generating a forecast. So that concludes our presentation. We'd be happy to take any questions.
Yeah, thank you for the presentation. We have some questions in the chat box by Waxton. Do you wanna ask this, or should I read it out? Otherwise, I read it out. Okay. So first question is, could you share this team size and analysis training time for this project to get a better notion of the effort?
Yes, I can definitely mention that. So if I understand correctly, the Waxton is referring to the amount of data that we worked with and what was the analysis and training time, right? So in terms of the products and time series, we worked with around 33,000 time series, where we went through the process of generating a weekly forecast and then a daily forecast. The analysis and training time, once we have the model and all its fine tuning done, takes around 2.5 to 3 hours for that data. As you can imagine, the most time consuming part is the neural network based model, right? So that's what takes the most amount of time. But in SAS, we utilize some high performance engines, which really makes use of parallelization, concurrency to really optimize performance. And by using those methodologies, we get around 2 to 3 hours to generate the weekly forecast. And for the daily forecast is probably on the order of like 1 hour or so to generate for the 33,000 time series. And so that is the amount of training time that it takes. And total effort, in terms of the effort, we have spent around 1 year or so total with this project over the last year or so, developing all these techniques and making this solution.
Okay, and this is, I think Waxton was asking also about, like, so 1 year is the time, and is this like a 5, 10, one-person project or an internship?
Oh yeah, So yeah, it was me and Varun primarily working on this for most of the time. We had a few folks just doing some data management, but yeah, most of the effort was spent
The
by
modeling was being done by
us.
us. And from the customer side too, I mean, this is a big change management, right? So we had a team of about 5 people from the customer side looking at the results and then providing some fine tuning. So there was quite a bit of learning along the way, but it'll be much more simpler for the next client for the implementation.
Correct.
Understood. If you want to, speak up for the participant and ask questions, please do so. Just unmute yourself, maybe switch on the camera. In the meantime, I will read out further questions here from the Q&A box. Fanny Reels is asking, for the daily forecast results that you showed, what disaggregation methods did you use? Was it the one using an ML model to predict daily proportions?
Yeah, so one of the models was the machine learning based models. So as we have kind of discussed these 3 models, so we used a total of 3 different models to disaggregate the weekly data to daily data. And so, yeah, and as we described, right, one model gets the proportions based on the previous 13 weeks of shipment, daily order shipments. Second model looks at the previous 3 years of daily order shipments. And the third one uses the machine learning based method to get those proportions.
Yeah, and if I may add, so we are using a champion model approach. So what we mean by that is, so we have a holdout testing time frame where we evaluate for every SKU location, which one of these 3 models perform the best, right? And the one model that performing the best, that's the one that is used. So for some SKU location, it could be the short-term trends that is much more valuable. So in that case, I will be using that. But in some of the other cases, it could be the machine learning model, which comes up with a better prediction over the testing time frame. And then we use that for disaggregation. So it varies across these 3 methods depending upon what is the best model that performance. Yeah. And also, I also saw a question from Waxton about the accuracy. Kedar, if you don't mind just going back to the accuracy slide pretty quickly,
Yes,
right?
yes.
We can
Yeah,
just
I think
show them.
There's a question also by Nikos Kourensis on this in the chat where he says there are some practical limitations of providing accuracy instead of error, also percentage metrics. So I think he's asking for further comments.
Right.
Yeah.
Yeah. So this is how we calculate the accuracy. And just to give a little more flavor into this, right? Yeah. So for a given lag period, right? There are these summations in the numerator and denominator. So let's say if you want lag number 0, we'll sum the errors associated with all the forecasts for lag 0 and divided by all the sum of the forecasts for that specific lag, and then do a 1 minus that ratio and multiply it by 100 to get the accuracy. And yeah, of course. And so just additional, so these are the measurements that the CPG company currently uses these metrics in their current methodology, right? So so they requested us to use the same metrics. Someone may have seen these similar accuracy measures where the denominator is the actual order quantity and not the forecasted quantity. But yeah, that's just what the CPG company uses, and we use that.
Yeah. And their logic was because, I mean, sometimes the actual values goes to 0. The forecast doesn't typically go to 0. So that's why in order to avoid the division by 0, they suggested using the forecast values. And just like Kedar said, just to be consistent, we just stuck to this. That's it.
Correct.
Okay, so there's a question from Skander, and I'm sorry, my Zoom skills aren't great. I'm trying to unmute him. Someone from the panel, can you try to unmute Skander? Tao, not sure if you can.
Yeah.
Hello?
Better.
Yeah.
Yeah. My question is around using inventory and POS data. In my experience, a lot of teams have been using that for quite a while to improve their forecasting accuracy. And when it gets to demand sensing and using modern machine learning techniques, the challenge I've faced is what are the features? Not can you include them in the model, but what are those features to start with? Once you get to that, then the model is pretty straightforward. So can you share any details around that?
So can you elaborate a bit more, like what kind of features are you looking?
Well, an example, not directly related to CPG forecasting, but for example, in airline industry in China, recovering from COVID-19, they went after downloads of travel apps as a leading indicator, right? So back to the original statement, you know, some of the teams I've worked on before, inventory data, out of stock POS data, that's been around for a while. The real challenge, especially with COVID-19 and the move from demand forecasting to demand sensing, which is how do you find these input features, not how do you include them in the model?
Yep. That's a great question, Skander. Yeah. And frankly, I mean, we have been doing a lot more analysis this year due to COVID-19, right? Unfortunately, we couldn't get permission to share that from the CPG company in this talk, so we didn't include that. Yeah, so like specifically, like, I mean, there are other demand sensing signals that are very relevant, especially now during COVID-19. One thing that SAS that we are currently working on, it was Google Trends data, right? We found that was very relevant because like in CPG specifically, if we noticed due to COVID-19, there was a lot of, immediately after a shutdown was announced, or work from home or shelter at home, there was a lot of pantry loading that was happening, right? And that was very regional effect. Depending upon the spread of COVID-19, it would vary quite a bit from East Coast to West Coast, right? So what we found was we started using the Google Trend information. That seemed to reflect fairly well. Like, so that was indicating when this lockdown would initiate, and then we're seeing a strong correlation to the point of sale, and then as a result, the shipment orders as a response to that. So that was one of the data that we included. Then epidemiological data, I mean, that was other thing that was strongly correlated, related to the spread at a high level in the region, like what kind of what is the prevalence of this disease from the Johns Hopkins universities, right? So there's some of the strong demand sensing signals, and the macro indicators are something in the normal circumstances that are good to include, right? And that was something. It could vary quite a bit from region to region. We didn't see too much of a strong effect due to this growth rate and so on in the analysis that we did, right? So that was why in our previous analysis it was not strongly included.
I think let me kind of dive a little bit deeper on that, in the sense that, you know, so first of all, thank you for sharing that, and a lot of it makes sense. But the question is, like, how many of these are really like relevant features, and how many of them get baked in and become endogenous to the time series very quickly, and like you don't really need to architect for all these features. You just need to wait a couple of weeks until it gets baked into the time series signal itself.
Yeah, so that's a good point. So that's why one of the features, right, Skander, that we use into the neural network model is actually the time series forecast and the trend, right? Because we know that if there is any kind of seasonal patterns that the time series model can pick up, that can be good features to include into the model. And the other one that we also mentioned was like the order history lags, right? So we look at the same for a given week over the last 4 years. We look at what the order history is historically, and we use that also as the inputs, right? And so, of course, like with this analysis, and we just want to mention, like, this analysis was all like pre-COVID. So a lot of these COVID-related effects, we did not include them or not incorporate them into the model, but those are kind of the main things that we found really helpful. Yeah.
Thank you.
One question I had was, so you mentioned that you used neural networks. What kind of neural network were you using, and how were you using them? There's a bit of I think growing awareness for using neural networks as sort of so-called global models, you know, where you learn across the entire set of time series, not just for a single time series. So I was wondering if you could, if you can, shed some more details on what type of neural network you're using and how.
So here we have used like a very simple neural network. It's like a single hidden layer neural network. And the main motivation here, of course, whenever we see time series and neural networks, what comes to your mind is like a recurrent neural network, right? Because like LSTMs and all these RNNs, which can really capture and been successful with like language data and so on. But we want to keep in mind, we don't want to make this product and spend a lot of time in training the models, because as you incorporate like a very heavy neural network with a lot of parameters, you have to spend that much more time fine-tuning those parameters. And honestly, like machine learning and neural nets are great, but CPG companies, like most of the time, if many people don't fully understand the inner workings of neural networks, and so if there is, and treat it like black boxes, you know. So that's the reason why we used a more or less a very simple neural network here, which we are confident that it doesn't take much time to train and can still be beneficial to generate a accurate forecast.
Sorry, if I can follow up on Tim's question, but we're making a lot of progress in AI explainability. So does that statement really hold in the long term?
Yeah, that's a great point. So, and of course, like AI explainability is great, but more, at least I feel more about explainability is to the CPG companies itself, right? We need to explain how these are, and the CPG company, at least with which we are working with, they are really interested in knowing exactly, because the main problem is like if we use a neural network and something goes wrong, like it's not able to predict, then the CPG company needs to be able to understand exactly what's going on in the model itself, so that they can better try to fix it.
Yeah, and absolutely. And I think that is one of the future phases that we plan to do, Skander. I think, and we feel that strongly, like over the next few years, right? There is a lot more confidence that will be built in the industry, right? In using the latest neural network models due to precisely this explainability that we can show that to them, right? Because especially from the operational folks, if they can't explain why and how, right, it becomes very difficult for them to adopt it, even though we can show metrics saying that is significant improvement in all the test analysis that we have done. But we are fairly optimistic over that we could see a lot more adoption of this happening over the future next few years.
We have, I think, time for one more question. And Tao, I'm not sure if you could unmute Thomas, who is asking a question in chat.
Yeah, and I just saw that question. I can maybe read it out. So did you have to handle new time series, that is new locations without past data, and how do you handle these normally? So that's a great question. So in the pre-processing phase, right, we did this segmentation of the time series where, of course, like with the machine learning model, you need to have enough data history in order to accurately predict into the future. There were some time series which did not have enough history. And so for those time series, we just used the classical time series based models, because there is no use, like you can't really use a machine learning model if you don't have, let's say, like past 4 years of order history available, right? So the pre-processing phase is where we do this segmentation. Automatically, we look at all the time series and we check how much data is available for each time series, and based on that, we determine which model to run. Yeah.
And if I may also add, at SAS, we have a product called as new product forecasting. And so essentially what that does is it looks for like products. Like if you are actually introducing a new product in the life cycle, and then there's a similar product that has been discontinued in the past, or with a similar product characteristics that is available to us, then we can automatically take the connections and borrow the history from that materials for the new products and forecast based on that. In this particular case, it was fairly a mature market with a good amount of order history. There were very few items which were like completely new, so we didn't have to do a lot of that. But that is a process that we do. The new product forecasting is typically that we use. There was no new locations as such, so it's all about new product introductions. Yeah, so that's the answer.
Yeah, Skander has an interesting comment, I think, in the chat box that, you know, especially for global models, machine learning based models have been, can also play a role for cold start problems, but we are at time. I want to be mindful of it. I want to thank everyone who participated in this lively discussion, but primarily Varun and Keda for your great presentation. And I wish everyone a very good continued ISF.
Yeah,
Goodbye.
thanks, Tim. Thanks a lot for asking the questions. Appreciate that. Bye.
Thank you very much. Thanks a lot.